Yeah, I think I'm gonna start. I'm gonna start, I think. Okay. All right. Hi, everybody. Welcome to our Calc 2 mid-semester review night. My name is Izzy. I'm from the MRC. This is Howard at Savannah. We're going to be going through a whole bunch of topics tonight. To be completely honest, we probably don't have time to go in depth through every single one. This is kind of set up so that we can ask you guys like, oh, do you want us to go through examples of this? Do we want to go further on this, or do we want to just skip past it? So please feel free to give us lots of feedback. Let us know which stuff you want to go more in depth on and which stuff you're good to just kind of skip over. But yeah, I think we're ready to go. All right, so we're going to start with some integration by parts. Woo! Everyone's favorite. So this is the form integration by parts takes. We call it ultraviolet voodoo. I also personally like to set it up as U equals a part of my equation, dV equals a part of my equation, du beneath it, v underneath that, and then you go like this, and then subtract that way. That's how I set it up personally. This acronym right here is a guide for you on how you should choose your U. So for example, if there's a natural log in your integral, then you're going to want to choose that first, and then the inverse, and then the polynomial, if, for example, like x squared or something like that. What it comes down to is that you're trying to take derivatives of part of your function to make it disappear. That's what you're trying to do ultimately, is to not have to integrate something that you can't really integrate. And so you take some derivatives and multiply it using this formula. I've got an example right here. So the integral of x squared times cosine of x. I'm going to choose my u to be equal to x squared because it's a polynomial. And so I know that as I take derivatives of it, it's going to essentially disappear, which means that my dv is going to be equal to the second half of the equation, which is cosine of x dx. Whoa, dx. And then my du, my derivative, is going to be 2x. And then v, my integral, is going to be sine of x.
Should we turn off these front lights? Yes.
Oh, yeah, that's a good idea.
On that.
Oh, wait, there we go. That's not what I wanted. Oh, there. That.
Or no, people are taking.
Yeah, fine.
I mean, this is not going that.
Good?
Like that's
Okay. Sure.
How about this one?
Wow. Sure.
That one?
Okay. Yeah. Okay.
perfect.
So then I'm going to multiply these two and then subtract by the integral of those two multiplied together. So this means my integral is equal to x squared sine of x minus the integral of 2x sine of x dx. Awesome. So now, as you can notice, I can't integrate 2x sine of x directly, which means I'm going to do it again. Hooray! I'm going to label these variables as u prime and v prime just so that they're different, but it doesn't really mean anything. U prime, I'm going to set it equal to 2x again, so that it'll disintegrate with the integral. And then my dv prime is going to be equal to sine of x dx. Whoa. Which means my du prime is going to be equal to 2, and my v prime is going to be equal to negative cosine of x. Nice job. So that means I'm going to have all of this stuff is still going to stay x squared sine of x. And keeping track of these negative signs is a spot where a lot of people make mistakes. So I like to leave everything in brackets and parentheses until the very end. So it's going to be minus negative 2x, whoa, 2x cosine of x minus the integral of -2 cosine of x dx. Yeah? So then when we distribute everything and integrate this last term, we get it equal to x squared sine of x plus 2x cosine of x from those two negatives right there. And then this one, keeping track of the subtraction is a little tricky, but the integral of -2 cosine of x is going to be equal to, I have to think about it sometimes, -2 sine of x, and then that negative makes it positive, sorry, this negative makes it +2 sine of x, and then this negative makes it again -2 sine of x. And that is our final answer. Do you guys have any questions about that process? Is that all familiar? Okay.
Example where we have to circular.
Yeah, we can, for sure. I have two more examples of integration by parts. There's this one, which is somewhat simpler, and then the next one is what he was talking about, where, spoiler alert, it's like circular. You have to do it a few times. Do you guys want me to go through this one, or do you want me to skip to the next one? Skip? Okay, sounds good. All right, e to the 4x times cosine of 2x. So some hints that maybe this is going to be one of the tricky ones where you have to do it a few times before it ends up working is the fact that it's a trig function and an e to the x function. They tend to do that. Because exponentials, as we know, the integral of an exponential mostly stays the same. Okay, so with this one, I'm going to set, if you remember back to our like lipta thing, our exponentials are last, because as we take derivatives of exponentials, there's a constant that's multiplied, but it basically stays the same. So we don't want to set those as our u. So instead, we're going to set our u equal to cosine of 2x, which means that our v, that doesn't make sense. Why'd they do that? Oh, I see. Which means our dv is equal to e to the 4x, which is just the other half of this equation. So then when we integrate it, we get 1/4 e to the 4x, right? And then our derivative of u is going to be -2 sine of 2x. Okay. So then when we do our ultraviolet voodoo, which in this case would be multiplying this way and then integrating that way, we get 1/4 e to the 4x cosine of 2x plus, this is 1/2, this 0.5 is 1/2 multiplied by 2, just makes it 0.5. And then because this is -2, the subtracting from the integral becomes positive. So 0.5 times e to the 4x sine of 2x. Okay? And once again, we have an exponential function and we have our trig function. Oh no. Looks like we're gonna have to do it again. Woo! Except this time, we're gonna have our u equal to sine of 2x, and then our dv equal to e to the 4x again. It's gonna be the same process, right? But we have to carry over all of this same stuff, and then this integral that we're solving, that just adds on to each other, right? Okay. So then all of this comes down to here again, and the 0.5, it still has to be multiplied through, right? And so we end up with our uv, which is 1/4 or 0.25 e to the 4x times sine of 2x minus our v du, which is going to be, again, 0.25 times 2, so -0.5 times the integral of e to the 4x cosine of 2x. Now this right here is the trickiest part to figure out. What can you guys tell me about this chunk right here? That specifically. It's the same thing as what we're solving for, right? Yes, which isn't true. Those are 2's. Yeah, those are supposed to be 2's. Good catch. Assuming that they had written down the problem statement right. This 0.5 cosine of 2x is the same. And we have set this whole integral up over here. And this equation works the same way as any algebraic expression, where we can add things over and subtract and divide just the same way, right? So then,
Got the five brackets.
yep, they multiplied that through, circled that, and then we move it over to this side, just like this, and get 5/4 times our original integral is equal to all of this jazz, okay? Which then means that our original integral will be equal to 4/5 times all of that jazz. Does the process make sense? I know there's a lot of in-between algebraic steps, but at this point, I'm more concerned with the overall process. Does that track for you guys? Yeah? Okay, awesome. Any questions about that or what we did? Okay, awesome. Howard's turn.
Alrighty. Rick's about to clip this onto. All right, cool. Partial fraction decomposition. Cool. So partial fraction decomposition is just a really easy way to simplify a complex fraction that is really hard to evaluate. That's basically the gist of it. And we'll go through a couple examples with it as well. This table just kind of shows you a little bit on how that works, some of the rules to go along with it. But we'll do some examples, and you guys can always refer back to this table. Can they download the slides? Are these slides downloadable? Are we going to share them anywhere? I don't think so. All right. Well, you guys can take a second to write these down. I'll stay on this slide for a second if you guys want to write them down, and then we'll do some examples. And we can decide how many we want to do based on how comfortable you guys are with them. So, is everybody ready to go to the next slide? We're gonna just wait. All right, cool. Sick. Why is it already showing the example? I don't like that. All right, fine. Since it's already showing the example, can they not? Shows the answer. Okay, so it shows the answer, doesn't show the steps. So I guess we'll just know what the answer is towards the end. I don't know why it's doing that, but we'll work through it. All right, so this one, x plus 1 over x plus 3 times x minus 2. So this would be a really ugly fraction to evaluate as an integral. So we're going to use partial fraction decomposition to make this a lot simpler. So to start off, we're going to break this up. So this fraction, the x plus 1 over the x plus 3 times the x minus 2. And I'm going to rewrite this, make that look a little bit better. So we can break this up, and we can basically say, okay, that is going to be equal to some value over x plus 3 plus some value b over x minus 2. That's the start of partial fraction decomposition. Now, at the bottom of this fraction are two separate values, the x plus 3 and the x plus 2. Those are two separate things, so we can just do this. But as you'll see in like a future example, and from the tables, if we had like, if this was like squared right here, then we'd have to do an x plus 3 squared down in the bottom and do another term that was x plus 3 as well, but we'll see that later. How do I erase on this thing? That's how. That makes this a lot nicer. Cool. So that's the start of our partial fraction decomposition. What would be the next step? Who could tell me the next step? Let's see what you guys know. All right, what do we do?
Be setting the, would it be making it so that the two terms on the right can be fully like combined together?
Yeah, and how would we do that?
We need to get them to have the same denominator, yes?
Same denominator, right? All right, cool. So how we're going to do that is we're going to cross multiply, right? The good old butterfly trick. At least that's how I did it in like elementary school or whatever. good old butterfly trick. So we're going to take our a and we're going to multiply it by x minus 2 to both the top and the bottom of that fraction to make it so that it has the same denominator as our left side. So we're going to take this a over the x plus 3, and we're going to multiply it by x minus 2 on the top and x minus 2 on the bottom. And that will mean that we have an ax minus 2a all over the x plus 3 times the x minus 2 on the bottom. Cool? Everybody following so far? All right, cool. Same thing, but now we're going to do it with the b. So we're going to have b over the x minus 2, and we're going to multiply that by x plus 3 on both the numerator and the denominator. Right? And once we do that, we're going to have bx plus 3b is equal to x plus 3 over x minus 2. That's a 3. Cool. Any questions so far? We good? We good with everything? How that's moving so far? All right. So now we'll go on to the next step, right? So now we have set our right side to have the same denominator as our left side. So that means that our a and b values are ax minus 2a and our bx plus 3b have to come together to equal the x minus 1 on the top on the left side. Does that make sense to everybody, how that works? Before I move on? We good? I'm not hearing any objections, so I'll keep going. So we're going to set our two numerators here and here equal to this numerator. And that's how we're going to solve for our a and our b. So we're going to have our ax plus ax minus 2a plus bx plus 3b is equal to an x minus 1. I mean, x plus 1. Right? So now we can combine like terms. So our a right here has an x with it, and our b right here has an x with it, and our x has a coefficient of 1. So that means that we can set our a x plus bx equals 1x, cancel all the x's, and we get a plus b is equal to 1. That's our first step of it, right? So then after we get that, we can do the same thing with our constant values. So we have our negative 2a, our plus 3b, and our plus 1. So that means we're going to have a negative 2a plus 3b equals 1. Cool so far? We good? Y'all good in the hood? All right, cool. So now we have a system of equations with two equations, two unknowns. We can solve for our a's and our b's. So the way I like to do this is I just like to set the top equation equal to the bottom of it, like set one term of the top equation equal to the sum term on the bottom of the equation. It's just gonna be easier to show you. So I'm gonna take this top equation, I'm gonna multiply it by 2. That's what I'm gonna do. I'm gonna write it down here right below it. So it's gonna be 2a plus 2b equals 2, right? All I did was take this top equation, multiply it by 2. That's all I did, make it nice and easy. And now we can add these two equations together. Our a's will cancel, those are gone. And we have that 5b is equal to 3, which means that b is equal to 3/5. Everybody see how I got that? Everybody agree? Cool. So if we have our b now, we can then use that to plug back into one of our equations and solve for a. I'm going to use the easier equation because that's what I like to do. If you guys like it hard, I guess you guys can do the harder equation, whatever floats your boat. So I'm plugging it back into the first equation, the a plus b equals 1. And solving for a here, we're going to get a is equal to 2/5. Everybody good so far? Cool. So now that we have that, we now know what our numerator is on our right side back here. We now know what our numerators are, and now we can evaluate them separately. So that's where this equation is going to kind of come in. We're going to do one step before we get to that, and then we'll just look at what's already up there. So we are then going to take that, and we're going to have our 2/5. Or actually, not, you guys can just look. It's right here. Yeah, so we're going to have our a back into here and our b back into here, and we're going to evaluate the integral separately. And that's going to equal this integral. I skipped a step there. Does everybody see how I got there? Everybody good on that? Cool. So then we can just evaluate this integral separately, and that will go to this. Does that make sense to everybody? How that example worked? All right, cool. Well, we'll go on to one more example, and we can do that if you guys want. This is just showing the steps. And I might as well clean this up so you guys can see them nice and easy. This is going to be a lot of erasing. You know what? Screw it. I'm not going to do that. You guys saw me do the example. All right. So now here's the next challenge problem. So what do you think, Izzy? Do you think I was planning to have them work through this by themselves, but we are limited on time. So what do you think? Do you guys want to work through it by yourselves real quick and see if you guys can do it, or do you guys just want me to do it with you? Just skip it? That works too. All right, that works for me. Cool. Then that's trig integrals. Do you guys want to do trig integrals too? No? Cool.
A lot of us are probably here.
Hey, that's fair. You guys tell us, right? Trapezoidal approximations, yay or nay? Cool. All right, well, I don't know where the content starts, so you guys are gonna have to tell me. Starts here? All right, cool. Who is this? Izzy.
My turn.
Works for me. Hey, you guys tell us what you guys need. I don't I have no skin in the game. I don't care.
Okay. Beep. Oop, I also want my iPad. Ugh.
Yeah. Want to go?
All right, party people. Let's talk about some series tests, yeah? Okay. So with our series tests, the main thing, these are two series that I would watch out for first, if that makes sense. And it comes down to what form the series takes. So if it's a sum of 1 over n, if n 1 over n sub p, if p is greater than 1, then it converges, less than 1 diverges, or equal to 1 diverges, yeah? And that's one that also comes up a lot when we're using comparison tests, because it's an easy one to make comparisons to, right? And as you can see, this is our graph of what the 1 over n graph looks like. Basically, if n is to a high power, then this graph converges to 0 fairly quickly. And so that's why it converges. The next one is our geometric series, which takes the form of a times r to the n minus 1. Something that comes up a lot is that if we have a times r to the n, that will be equal to a times r to the n minus 1, right? So if we need to set it into the form of a times r to the n minus 1, we make that substitution a lot. This one is cool because if r is less than 1, then we actually know what it converges to, which is kind of crazy. Not a lot of tests tell us that. And this is kind of a graph showing what they end up looking like, where our squares are just getting smaller and smaller and smaller, right? Okay. And here are the actual tests written out. That's my bad. I didn't know I did that. Okay, cool. The next kind of easy one, we're going to talk about the integral test. We have 3 main conditions for the integral test. If a sub n is equal to, or like approximately, a function, and the function is continuous over where we are summing up all the values, and it's positive, and it's decreasing, which we can test that by finding the derivative of our function and seeing if it's less than 0, right? If all 3 of those things are true, then we know that if the integral converges, the sum converges, and if the integral diverges, the sum diverges, right? Because we're basically saying if all 3 of those things are true, then the integral and the sum are basically doing the same thing, right? Okay. Cool, cool, cool. Do you guys want to go through this example or skip? Yes, do it? Okay. Okay, cool, cool, cool. Basically, all I'm doing with this one is I'm saying that my f of x is equal to e to the negative 5x, right? So I check, is it continuous? Because we're going from 1 to infinity, it's continuous there. Is it positive? Yes, it's positive. And then my derivative of f of x would be equal to negative 5 e to the negative 5x, which is negative, which means that it's decreasing. Perfect. This means I can use the integral test. So now if I integrate e to the negative 5x dx, dx, then that gives me negative 1/5 e to the negative 5x, evaluated from my bounds 1 to infinity. This is technically a limit where we're doing like b and then b is equal to infinity, but I think you guys get the gist without the notation. And so then if I plug in infinity to negative 1/5, where e to the 5x is on the bottom, as I plug in infinity for x, my denominator is going to get infinitely big, which means that my overall fraction is going to get infinitely small and be basically 0, right? And that's what we're saying when we say a limit, it's basically 0. So that means the only thing left is going to be minus negative 1/5 e to the negative 5, because I'm just going to plug in 1 for my other bound. And then because this is an actual number and it's not infinity, then I know that it converges, which means because I tested all of these things, that my series also converges. Does that all make sense? Cool. Oh, there's the steps. Okay. Do you want me to do another one or skip? Skip. Okay. Cool. Direct comparison test. Woo! Everyone's favorite ever. Okay. So basically what the direct comparison test is saying is that if I have, yeah, for sure. No, thanks for saying that, for sure. Yeah. Basically what the direct comparison test is saying is that if I have a sum that I can represent as something like this, and I know that it converges to some value, okay? And then I can prove that this is always going to be greater than my other function, then I know that this one, it's kind of like it's capping it. It's not letting it diverge. It's always going to be greater than it, so it's not letting it jump past it and diverge, if that makes sense. And then the opposite can be said for if I have a function that kind of goes like that, where it diverges to infinity. And then I have a function that I know is always greater than it, then this one you can think of it as like it's pushing it up. And it's not letting it converge, it's forcing it to diverge, is a way of thinking about it. When we're doing direct comparison tests, there's kind of 2 steps. We need to prove that b sub n, which is the thing that we choose as our function that's pushing it or capping it, we need to prove that b sub n is less than or greater than our original sum, right? And then we also need to prove that b sub n either converges or diverges. So if b sub n converges and it's greater than our original sum, then we know that our original sum will also converge. And then if b sub n is, did I say that backwards? No, yes. And then if b sub n is less than our a sub n, our sum of a sub n, and it diverges, then a sub n will also diverge, is what all this is saying. Yeah? Okay, so then let's do an example problem. And I'll give you a hint. This one's got a sneaky other test in there that we're also going to do. Okay? So when I am thinking about what to choose as my b sub n, what I think about is a lot of times I look at these denominators and numerators, and if there's like plus some constant in either case, it's pretty easy for me to prove For example, for a crazy example, that 3/7 to the n is always going to be is always going to be greater than 3 to the n over 7 to the n plus 8. Because my denominator in this case is bigger, which means that my overall fraction is going to be smaller, right? That's a tricky one, but a tricky way to think about it. But anytime that you have a function and there's a plus a constant in the denominator, an easy way to look at it is to focus just on the part that's changing over time. And if you know if that converges or diverges, you can use that to prove the convergence or divergence of your overall series. So I'm going to set b sub n equal to 3/7 to the n, which is also equal to 3 to the n over 7 to the n, right? I'm just distributing that exponent, okay? And like I just proved, we know that b sub n is going to be greater than 8 sub n in this case, right? My 3/7 to the n is going to be greater than 3 to the n over 7 to the n plus 8, right? Just slightly, just slightly. So now I need to prove if b sub n converges or diverges, right? So I'm going to take the sum of 3/7 to the n from n equals 1 to infinity, right? And I need to prove if that converges or diverges. What test do you guys think I should use to prove the convergence of that series? Geometric. Yes, you guys are so smart. Okay. So I'm going to rewrite this, like I hinted to earlier, as 3/7 times 3/7 to the n minus 1, right? And I can do that because when we multiply two things with exponents, we add their exponents together, right, if they have the same base. So you can think of this as 3/7 to the 1 times 3/7 to the n minus 1. When you add those two together, you just get n, right? Okay. So then according to the geometric series test, if this was in the form of a times r to the n, my r in this case would be 3/7, right? And then because my r is going to be less than 1, that means that by the geometric series test, my sum of b sub n is going to converge. Did that make sense? Okay, awesome. So then, if I know b sub n converges and it's greater than a sub n, that means that by the direct comparison test, that the sum of a sub n will also converge. Did that track for everybody? Any questions about what I did? No? Okay. Awesome. Cool. There's my work. It doesn't matter. Okay. Do you guys want me to try and find another direct comparison test example real fast, or do you want to move to limit comparison test? Move on? Okay, awesome. All right, so the limit comparison test. This is somewhat similar to the direct comparison test in that we have to choose our own b sub n and then see if it converges or diverges. Usually the limit comparison test is good for like fractions with polynomials, if that makes sense. So like anytime you've got, I haven't actually worked out that example, but anytime you've got this kind of stuff going on, that usually means it's going to be a good limit comparison test example, okay? Basically what the limit comparison test is saying is that if we take our original series, divide it by the one that we're deciding, and we take the limit and it doesn't equal 0, then they either both converge or diverge. If it equals 0, then we can say they both converge. If one converges, the other converges. Or if it equals infinity, we can say if one diverges, the other diverges. Usually we're shooting for the doesn't equal 0, because that's the one that'll tell us for sure what's going on, right? So usually what we want to do is choose a b sub n so that the order of the numerator and denominator are the same. I know that was a lot of words. Basically all I'm saying is that if you guys remember the rule, for example, the limit as n goes to infinity of n to the 4th plus n plus 2 divided by 3n to the 4th is going to be equal to 1/3, right? Because my coefficients on these two will be 1/3. You could work through L'Hopital's rule and you'll end up in the same place. So this is kind of like a little shortcut that we do. So usually this is what we're aiming for, is for them, the numerator and denominator, to have the same order. Okay. All right. So we're going to go through this little example. Pretend you can't see the answer. So looking at this series right here, what I want is to set a b sub n so that this top part right here is also to the 4th. Okay, so I can take a really easy limit. So if I set my b sub n equal to 1/n, that means that when I divide it, if I divide by 1/n, I just get n, right? Multiplying by n, which is what I want. Because if I take the limit, n goes to infinity, of a sub n over b sub n, that will give me n to the 4th divided by 2n to the 4th minus 10n to the 3rd, right? And then what would be my limit as that goes to infinity? 1/2, exactly, which does not equal 0. Hooray! That's awesome. So now, if we know, we need to figure out, does the series of b sub n converge or diverge? Because whatever b sub n is doing, a sub n is also doing. So will this 1/n converge or diverge? What do you guys think? It'll diverge, right? By p-test, it's a harmonic series, whatever. Okay, awesome. Which then means if this diverges, my b sub n diverges, then my a sub n also diverges. Does that all track? Yes. Yeah? Okay. Moving on. Okay. I have, yes. Uh-huh.
We're trying to get it so if it doesn't equal 0 or
Yeah.
if we were to go up 0, then
If for that specific problem, if we set it up and we got a limit equal to 0, because b sub n diverges, that doesn't tell us anything. It's inconclusive. Versus if b sub n converged and we got a limit equal to 0, then they would both converge. So you can work it so that it's equal to 0 or infinity. It's just if it like converges or diverges, doesn't match up, then it doesn't tell you anything. So that's why we're usually shooting for this. But either way will work. Does that make sense?
if it doesn't, then only if on the n diverges.
Yeah, exactly. Totally. So it depends on the problem. You might, with these problems in general, you might have to try a few different things. I usually start with like Is it one of the ones that I can recognize, like the geometric series, the harmonic series, like roots, that kind of stuff? And then if not, usually the integral test, and then if not, these comparison tests. That's usually how I work personally. And sometimes I do have to try a few different B sub n's, a few different comparison tests. It's just kind of how this section is, unfortunately.
Say, hey, this looks like the harmonic series, you're not that. Have to make sure you use a test.
Which in that case would be the p-test, right?
Yeah.
Okay.
Use compare.
Yeah. Okay. Any more questions about limit comparison? Okay. This is a challenge problem that we can work through if you guys want. We can also, if you guys want to work on it, and then we can like walk around and you can ask us questions, we can also do that. Or I can skip it. What are you guys feeling? What do you think? I got one skip it. Anyone want me to work it out? Don't be shy. Let's work it out? Okay. Awesome. This one's a little bit tricky. It's a little tricky, but I believe in us, okay? Okay, so looking at this, it's not really a geometric series. It's pretty complex. I don't think my integral, I don't want to do the integral test because that integral is going to be nasty, nasty, okay? Yeah, thank you. Howard, do you mind shutting? Thanks. So I am going to use a direct comparison test. That's the first thing I'm going to try. So to use my direct comparison test, I have to figure out what my B sub n is going to be equal to, right? So when I'm finding my B sub n, I'm basically trying to simplify this series into something that I'm more familiar with. So I can say that e to the negative n over n plus cosine squared of n. I know that cosine squared of n, it's going to oscillate between 1 and 0, right? Because it's a cosine squared function. So it's never going to be negative, and it's just going to go between 0 and 1 the whole time. Which means that I can say that this whole kit and caboodle is going to be less than e to the negative n over n, right? Because e to the negative n over n plus 1 is always going to be less than e to the negative n over n, right? Does everyone track that step? Okay. And then I also know that e to the negative n over n is always going to be less than or equal to e to the negative n, right? Because this n on the denominator is going to make it decrease faster than just e to the negative n. So now, using this logic, I can set my B sub n equal to e to the negative n. Yes? No, you're fine. Do you get it, or do you want me to go over it? Because it's less than or equal to. Yes, exactly. Okay. Which less than in the or equal to's, totally legal in the comparison test. Okay. Awesome. Okay. So now I want to prove the convergence or divergence of e to the negative n. This is where I'm going to use the integral test. Okay. So I can say that e to the negative n is basically the same thing as e to the negative x, right? E to the negative x is continuous. Check. E to the negative x is positive. Check. And then the derivative of e to the negative x would be negative e to the negative x, which is negative, which means that it's decreasing. Check. Boom. Integral test, totally legal. Let's go. So now I need to find out if the integral of e to the negative x diverges or converges, right? So I'm going to take the integral of e to the negative x dx from, what are my bounds? 2 to infinity, okay? My integral of e to the negative x is going to be negative e to the negative x evaluated from 2 to infinity. As I put infinity into this e to the negative x function, what is that approximately equal to? 0, nada, okay? So that means this is going to be 0 minus negative e to the negative 2, which is just like some number. Yes? As it's going to infinity, like as a function? Yeah, it's like that, basically, if that makes sense. Or actually, it's negative, so it's probably like, yeah, so it's from the bottom. Yeah, because 1 over infinity, basically 0, right? And it'll never actually reach 0, but it'll get pretty darn close. Yeah, okay, awesome. So then I can say, by the integral test, my sum of b sub n converges. And then, because b sub n is, I've already proved that b sub n is greater than a sub n, that means that my sum of a sub n also converges. Did that all make sense? Yes. Okay. So this is a tricky example where you go through 3 or 4 things, but did all those steps make sense? Cool. Awesome. All right. Alternating series. This is another one of those like special cases / like this is just a formula you kind of have to recognize, like, oh, that's going to be an alternating series. Basically, all that's going on is we've got like some function going on and then these values that are getting closer and closer to 0. If our series is converging, that's what it's doing, is it's basically getting squeezed closer and closer to 0 and alternating between those two. So that's what an alternating series looks like. And again, you might have to do this like this n and n sub n plus 1 thing over here. It doesn't really matter when we're talking about the overall convergence, but you can mess around with it. So our alternating series will converge if b sub n, meaning if our original series is -1 to the n times b sub n, whatever b sub n is, if it's basically the same thing as a function, and that function is continuous, and b sub n is decreasing, which again we can find by saying if that function's derivative is negative, then it's going to be decreasing. And that limit as b sub n goes to infinity is equal to 0, then we know it converges. Okay? And what all that is saying is what I was showing you earlier, where it's going like this, and then getting closer and closer to 0 and converging. Or closer and closer to some other number, but it's converging. Yes? Did I lie?
That's how you do integral test. For the integral test, you need to check all those conditions. And then if those conditions are checked, then you can do the integral. For the alternating series test, what we're saying is, hey, if I have this alternating series, if these conditions are met, then it converges converges. If they're not met, then it is not converging.
Yeah, so we don't know what it is. So I think
Mm-hmm.
on the sheet that there.
So essentially, you have to meet all
Yeah,
the
so-
conditions for it to be conditionally convergent, otherwise it diverges, and then we have to run another test to see if it is
Yeah.
absolutely convergent.
We'll get to absolutely convergent. Yeah, that's kind of a different thing.
then you need to run a different test and prove it diverges.
Okay, so it doesn't prove that it diverges, it shows that this can show
Yes.
that it can.
Yeah, so the alternating series test either proves conditional convergence or it's inconclusive. If it's
Okay.
inconclusive, then you need to go show it diverges by something like the divergence test probably.
Mm-hmm.
And then if it's conditionally convergent, you need to go test the absolute values of series and see if it's absolutely convergent too.
Yes. So speaking of absolute convergence, how it was explained to me by a friend with absolute convergence is this is kind of like the stability of the system, meaning that if it stops alternating, is it still going to converge, is kind of what it's saying, which is useful to know in some electrical applications. Fun facts. But basically, we also want to test our alternating series for if they absolutely converge. A series absolutely converges if the absolute value of the series also converges. Meaning if we get rid of the alternating part and just leave it as a 1, is it still going to converge? And proving that it converges absolutely, a lot of times we've got to use like just any of the other previous convergence tests we've talked about. Sometimes it's a direct comparison, sometimes it's an integral, all that kind of jazz. If this diverges, then it's not absolutely convergent. So, but it can still be conditionally convergent, but not absolutely convergent. It's kind of one step further, if that makes sense. Okay? Yeah. So we can go through this example. Yeah? Awesome. Okay. So we are going to determine whether this one converges or diverges. So the first thing I'm going to do is go through my little list of checks. So in this, if I factor out my -1 times n plus 1, my a sub n is going to be equal to 1 over n squared, right? I just kind of factored it out, and all I was left with was 1 over n squared. 1 over n squared is basically the same thing as 1 over x squared, which is continuous. Check. And I also know that the derivative of 1 over x squared, I'll do it this way, is equal to -2x to the -3rd, which is less than 0, which means it's decreasing. Check. Yeah? And so now if I evaluate the limit as n approaches infinity of my a sub n, then I'm going to get 0. Check. So all of this means that by the alternating series test, all of that jazz converges. Yeah? Does that all track? Okay. I'm going to test for absolute convergence next. Yes, that was my plan. Perfect. Okay, so just like you said, now we're going to test if this is absolutely convergent or conditionally convergent. So to do that, I'm going to test the sum of the absolute value of my series, which is going to be equal to the sum of 1 over n squared, right? If I take the absolute value of all of this, that's what I get, right? And then to prove that this series is convergent, I'm just going to use the p-test. Because p is greater than 1, then by the p-test, oh my gosh, the sum over 1 over n squared converges, which means that my series is absolutely convergent. Yeah. What would happen if I did this and it turns out that it diverges? It would be conditionally convergent, meaning it's only really convergent as long as it's still alternating, right? Okay. Awesome. Any more questions on that? On our series tests in general, alternating series, we're all good? Okay.
Okay, now we're gonna look at the Taylor and Maclaurin series, right? Yes. Do you have a question back here?
I thought we were talking about if it failed one of those conditions, then I thought we were like, hey, we don't know if it could diverge or it couldn't.
Yeah, that is correct. That is just why you need to run a different test. And like 99% of the time that test is gonna tell you a diverge.
Okay.
Is that fair enough?
Yeah. So it's just like because like if we were to do that and one of those tests failed, it could still converge.
Yeah.
Not like it's like a very small chance that it would converge.
Yeah.
But it's still.
Yeah, I don't have like a PhD in that or anything, but I want to say that if your alternating series test fails, that you're almost guaranteed that the six gonna diverge.
Okay.
Because if your limit doesn't equal 0, if that's the condition that causes it to fail, then you're gonna be summing terms forever, which is gonna cause it to diverge, right? You're gonna have infinite growing sum. And so that's why it's gonna diverge more often if that fails. Have another question?
Yes, I just wanna like clarify, double check. Only alternating series are gonna be conditionally convergent. Oh. Yeah. I wanted to say that. Cause it's alternating series. It's essentially a term that we made up for alternation. Right. Wait, aren't they also only the only ones that are also absolutely convergent? They all be absolute.
No, absolute convergence. Okay, absolute convergence occurs when you just take the absolute value of the series. So if you've got a funky series, max and absolute values on it, and you're like, well, does the absolute value of this thing converge? Then you're like, well, yeah, it does. So it's absolute. It doesn't matter if it's positive or negative, the six there.
Yeah.
Okay. Okay.
Are there any more questions before we move on to the next thing? Okay, awesome. So Taylor and Maclaurin series, mostly Taylor series. Maclaurin is just a special name for a Taylor series where A equals 0. So you'll mostly refer to it as the Taylor series, and the Taylor series helps us to approximate a function near a chosen point. And then as we add more terms to our series, right, it gets more and more accurate. So that's what we're doing, right? We're just approximating, and then at some point for these problems that we're doing by hand, we're like, okay, we have to have a cutoff point somewhere. We're just going to do 3 terms, 2 terms, right? We can't go on forever. So all of these are approximations. And then, like I said, right, we don't go on forever. We normally just do the first few terms. And then this is the expanded summation to that second order, right? Notice we start at n equals 0. So a second order Taylor series will actually have kind of 3 chunks or sections to it, but we have that second order where n is equal to 2, even though we have 3 terms, right? Because we're starting at n equals 0. And then, like I previously said, the Maclaurin series, right? It's the same exact equation or formula for the Taylor series. It's just a special name where a equals 0. So it's just a special name for that one. I'd say the best way to get into this is just to, practice assembling all our pieces. So we have our problem statement will often be something like, use a Taylor series to find the blank order of approximation, right? In this case, it's asking for the second, where n equals 2. And then from there, what we have to do is we have to know how to use our Taylor series. So I'd say Taylor series is something that will come up a lot in your engineering degree. So it's a good one to kind of just get familiar with and try and remember how to just write it out. Does anyone, it's on the last slide, but does anyone remember either the summation notation or expanding it out to the second order? You wrote it down? Nice. Okay. So yeah, good one to memorize, right? We have our derivative, right? However many orders of derivatives we need to take evaluating a. Our x minus a raised to that nth derivative over n. And then again, it's important that we start at n equals 0. Okay, so for the second order, I'm going to write out, right, because n equals 0 is our first term, right, it just all simplifies down to f of a. And then our second term is, right, that first derivative, n equals 1 of a. X minus a, that stays the same in the parentheses, raised to the power of 1, right? So that I won't write that out. And then all over 1 factorial, which is also 1. Then we do the same thing for the this third term. We have the second derivative, x minus a, raised to the power of 2 over n factorial, which is just, or over 2 factorial, which is just 2, right? So I'd say every time you see Taylor series, I want you to write the whole thing out first, because that just tells us what pieces we need to collect. Because a lot of this is just, okay, what do I need? And then we're all just going to plug it in at the end, right? So this is just telling me what do I need to go searching for. So I'm going to start with, we have our expression for f of x. And then I'm going to just write that out again, equals 4x squared plus ln 3x. And I know I'm going to need the first and second derivatives of this expression, right? So I'm going to take the first derivative, which is going to be 8x plus 1 over x. Is everything looking good so far? Okay. Then we could take the second derivative of x still equals 8 minus 1 over x squared. Yes. So if we break it down, right, we do the chain rule, it will end up canceling out. We do 1 over 3x multiplied by the derivative of the inside, which is just the 3. So that'll end up canceling. But nice catch. If there's anything more complicated, right, we'd want to slow that step down, break it down. But that'll cancel. Okay, but now notice we need f of all of these expressions evaluated at a. So that's what I'm going to do next, is plug in our a, which they gave us up here, a equals 2. That's what you're normally going to be given in a, except for if it's Maclaurin series, a is going to be 0. Yeah, so f of 2 equals 4 times 4, which is 16, plus ln of 6. And then we evaluate the first derivative, equals plus 1/2. Evaluate the second derivative, oh my gosh, equal 2 equals 8 minus 1/4. Right, so now we've just got all our pieces, and now we just all have to assemble it back into our initial expression. So we have this first term, f of a, which is we found to be 16 plus ln. Okay, I want that. 16. Okay, then we have the first derivative. Oh, yes, you're right. All the sixes. Okay. And then plugging in our next piece, right? F of first derivative evaluated at 2 is 16 plus 1/2, which should just be 33 halves. And then we need to make sure we have our x minus 2. Since we know what a is, we put that 2 in. And then finally plug in our last piece, 8 minus 1/4, which is 7.75 times 4. I don't quite know what that is, so I'm just gonna keep that here for now. And then we have our x minus 2 squared over 2. And then that should be our final answer. So a lot of these Taylor and Maclaurin series, right, it's just kind of knowing what expression we need, being able to write it out, and then assemble all our pieces to plug back in. So it's just very methodical, step by step. Yes. Mm-hmm. Right.
Is that 0, like when n equals 0, or is that just like 1?
Is so the fifth.
Like, you did the negative 2x.
Uh-huh.
Centered. It was actually the first series.
Okay.
It said to write the fifth Taylor
Polynomial.
out. Would that be
Yeah, into the 6 or into the 5.
like end of the 0? Was that incorporated? Like where it
X to the 5. Okay, yeah, that's makes sense because you want the polynomial to the 5th, so it'll be n to this, or we do it 6 times, right? Technically n to the 6, but you go until the polynomial has the 5th. So yeah, that's a good question. So yeah, it kind of just depends on the wording of how they're asking for these things too. Are there any more questions? Before, let's see. Have you guys, improper integrals, it's just kind of, right, you have to express it as a limit instead of actually plugging infinity into the integral, but then we can evaluate from there. Is this good? Do you guys want to go over this? Or is there anything else you really want to go back to? Or how are we feeling? Because I think this is the end of the, oh, no. Yes, power series. Okay, we are not at the end. We shall transition.
Sick.
Awesome.
Sick. Alrighty. Power series. Let's do it. All right, this is the last series that we have on our slide. So if there are any other series, we don't know about them, I guess. But I'm pretty sure this is the last one that we need to cover. So power series. So I just put a couple definitions up here. So first off, the definition is any series in the form where it has a constant and it's followed by x to the n power. That's basically what a power series is defined as. So down below that, you can see a power series centered at the form of a. So that's a power series centered at x equals a. So that's just how you implement it into the series. And then you talk about the convergence of the power series there on the bottom left. So the series converges at x equals a. It diverges for all x does not equal a. That is one way it can. The series converges for all real numbers x, or the series exists a real number r is greater than 0. You guys can read it. But basically, it's talking about the radius of convergence for that last one. So that's just basically what a power series is, just the gist of it. Now we have a couple of examples that we can do. So we'll start with this one. Also, this one I was planning to do together, and the next one I was having you guys planning to do on your own. If you guys want, we can just work through it together as well. I don't really care. It's your guys' review. So work through this example. So to start out, one thing that we're going to do with the power series is we're going to do the ratio test. So who remembers what the ratio test is? You guys kind of remember what that is? I'm assuming you guys have gone over that, yeah? Right? Cool. Yeah, so I'll write it out right here. Right? So the ratio test. Right? What up? The absolute value of the, yes, we do. Yes, we do. Thank you. Thank you, thank you, thank you. And these are not exponents, these are base. There we go. Yeah. And oh wait, gosh dang, it's supposed to be n plus 1 on the top. Hold on. I am messing this up. There we go. All right, cool. There we go. Ratio test. That's how we're going to start this one. So we're going to apply the ratio test to this series to start solving for it to see if it converges or not. So we're going to have our x to the n plus 1 over n plus 1 factorial all over x to the n over n factorial. All right? Cool. After that, that basically is going to go to this. It's going to go to x to the n plus 1 over. Now, n plus 1 factorial, what can that break down into to make this a lot easier? Right? So it'll be n plus 1 times n factorial, right? Is that what that breaks down into? Cool. Fraction divided by a fraction, you multiply it by the reciprocal, right? So it's going to be multiplied by n factorial over x to the n. Everybody see that? Cool? We good? Sick. So we can cancel out our n factorials here. And x to the n plus 1, is that not the same thing as x to the n times x? Theoretically, right? So cancel that x to the n's, and we're just left. That will then go to, we have x over n plus 1. Does everybody see where we got that final solution from, the x over n plus 1 from? Everybody follow? Cool. All right, so now to tell if that converges or not. So if we want to tell if it converges or not, what do we need to do? Right? So we take the x out, and then we take the limit as n approaches. What the heck was that? As n approaches infinity. Thank you. It's not that hard. 1 over n plus 1. Cool. So that's what we have. So what does that mean? Well, as n approaches infinity, we're going to start approaching undefined. That's not very good, right? Because it's going to be 1. Oh, wait, no. No, as n approaches infinity, it's going to approach 0. That's what it is. My fault. Yeah, as n approaches infinity, it's going to approach 0. Yeah, my fault. But, right, if we have x, right, so as n approaches infinity, it's going to equal 0, which means what? What can y'all tell me from that? Right? So as n approaches infinity, right, x is going to go to 0. Whatever x is, the value that's evaluated at is going to go to 0, right? It doesn't matter what x is. It could be anything. So since x can be literally anything, it'll go to 0, right? And that's how I'm going to write that. X can be literally anything. It'll go to 0. That means that x will converge for every value possible. Does that make sense? Doesn't matter what x is. It could be positive infinity, negative infinity. Doesn't matter. It will go to 0 as n approaches infinity, right? Everybody see that? Everybody cool? What up?
So, if we were to get a number, say we got like 4x or something like that, and it's maybe 4x, then would you just like solve for the inequality by doing -2 x, right?
Yeah.
-2 is less than x.
Yeah, I'm pretty sure, yeah. That sounds right. So you're saying like if this limit evaluated to 4, right? So it'd be like 4x or whatever. That's what you're saying. And then that means that the radius of convergence will be that. I think that's right. Is that right? Right? Or it should be 1/4, right?
Because you always evaluate the interval less than 1. The absolute value.
Right. Yeah. Right. So in order for this to converge, right? Once you apply the ratio test, you have once you apply thank you. Once you apply the ratio test, right? You want that value to be less than 1. That's how you can get it to converge if the value is less than 1. Because if it's greater than 1, it's just going to go off to infinity or go off to negative infinity. And if it is 1, then it's a special case and you have to test for it. So hold on. I think my next example actually goes over that. Let me double check here. My next example goes over that. Infinity. It's infinity, right? Negative infinity to positive infinity, infinity.
When it's 0 case, 0 is always less than 1, and therefore any is inverted.
Yep. Yeah. Doesn't matter what x is, any value of x evaluated like that will be less than 1. Yeah. So here, we'll do this next example, and I think that'll clear up a lot of questions for this next one. All right. So this one's a lot more complicated, but it's fun. This one's fun. It's fun. All right, cool. Same deal. We're gonna. Do you guys want to work through this by yourselves, or do you want me to work through it with you? All right. Cool. We'll work through it with me. All right, cool. Ratio test again, right? We like the ratio test when it goes to power series. That's what we like. Makes it nice and easy. So let's apply it. So we're gonna have. I'll do it step by step. I was thinking about skipping steps. We're just gonna do it step by step. All right. So we're gonna have an x minus 2 to the n plus 1 over n plus, okay, we'll just do that. N plus 2, 3 to the n. Why does you keep doing that? Stop doing that. 3 to the n plus 1. Cool. Double check that that aligns with my notes. It does. All right, cool. And that's going to be all over x minus 2 to the n over n plus 1 times 3 to the n. Cool. By the ratio test, sick. That means it's going to be x minus 2 to the n plus 1 over, figure out how I slide this the best way. Okay, over n plus 2. 3 to the n plus 1, that's just 3 to the n times 3, right? So that's how I'm going to write it, just so that it's easier to cancel stuff. Then we're going to have n plus 1, 3 to the n, over x minus 2 to the n. All right, now we can cancel. So that goes away. We still have an x minus 2 on the numerator there. Right, and then the 3 minus n's, they will cancel. And the x minus 2 over here will cancel with the numerator 1. So after all the canceling, we should then have x minus 2 times n plus 1 over 3n plus 2. Right? Is that right? Yeah, that's right. All right, cool. So now we apply our limit again, right? So we take our limit of that as n approaches infinity, right? So go here. Hopefully I don't run out of room here. Why do you keep doing that? So the limit as n approaches infinity of that. That's just going to be infinity over infinity. That's going to equal 1. Doesn't really matter, right? Because it's just going to be n over n, basically. It's going to go towards 1. That's what it's going to approach. Does everybody see that? Does everybody see that? I want to make sure everybody sees that before I move on, right? We're pulling out. We'll pull out the x minus 2 over 3. So here, we'll do this step by step. Well, I'll do it step by step just so you guys can see. All right, so we have right? So as n gets increasingly big, right? If you have like 50 million over 50 million plus 1, that's basically 1, right? So it'll approach 1 as n approaches infinity. So that's going to equal 1. Does that make sense to everybody? Cool. So that'll equal 1, which means that it is going to be equal to x minus 2 over 3.
The out has an absolute value. Like if it was -3, would you pull a -3 out, or would you pull a 3 out? It's the limit. Is the limit.
Be the absolute value, yeah.
So you pull a 3 out no matter what. If it's,
Yeah. Yeah, you pull a 3 out.
absolute value.
Good? Cool. All right, so now this is our limit, right? So in order for this to converge, after we apply the ratio test, what does the absolute value need to be less than? 1, right? But what if it's equal to 1? Then you have to test for it. And that's what we're going to have to do in this problem. So equal to 1, maybe. So is everybody good to where we are right here? Because I'm going to erase, because I have to erase this and get more room. Unless I can add a slide somehow real quick. Do you think so? Or should I just erase? All right, we're going to do that. I'm going to add a slide. New slide. All right, cool. That's what we're going to do. All right. Where's it? Why is this not working? Come on. There we go. All right, let me go back to that. All right, you know what? I think I just erased my work anyway, so. Oh, well, it'll be fine. All right, 1 second. Okay, and we're almost there. There we go. All right, cool. So back to where we were, right? After we applied the ratio test, we had x minus 2 over 3, and it was the absolute value of that. That's what we had. So now we have to test for convergence with that, right? We know it'll converge when it is less than 1, and when it's equal to 1, we have to test for it. So when it is less than 1, what will our convergence be for x there? Right? Because if it's the absolute value, that also means that, right? Does that make sense to everybody? Does that make sense to everybody? I want to make sure that it makes sense before we move. All right, cool. So now we have that, which means our interval of convergence for x is going to be what? If we were to solve for that for x, what is x going to be? -1 to 5? All right, well, let's see. Let's work through it. So we have -3 less than x minus 2, which is less than +3. We add 2 to both of them, right? Which is going to go to a -1 less than x less than 5, right? So -1 to 5, just like you said. Yep. So that right up here, the absolute value is less than 1. We get rid of that absolute value because, right, that absolute value, it could be anywhere from -1 to +1, right? That's what the absolute value is saying, is that no matter what it is, negative or positive, it has to be less than 1. So it could be -0.99999 repeating. The absolute value just makes it, so it has to be less than 1. So when we get rid of the absolute value, it just has to be greater than the -1. Does that make sense? Right? Cool. So that's where we got rid of the absolute value from. That's where you get the interval from the absolute value. So once we're here, right? So this is our interval of convergence, but now we have to test to see, okay, does it converge at 5 and does it converge at 1? Right? So this is where it gets fun. So now we're going to go back to our original series and we're going to plug in -1 and we're going to plug in 5. Right? So let's go ahead and do that. So we're going to have so this one will be the test for -1. So we're going to have the summation as from n equals 0 to infinity. Okay. Of where was I getting that value from? Oh, that's where I was getting it from. All right, cool. And that's going to be, we'll test, I can't tell if this is testing -1 first or not. I think it's testing. This one's testing -1. All right, yeah. So we're gonna test -1 first, right? Testing -1. So we're gonna have a -3 to the n over n plus 1 to the 3n. Okay? We can simplify that a little bit because negative 3 to the n is just negative 1, 3 to the n, right? So, or negative 1 to the n times negative 1 to the n, no, I'm just going to write it out. So negative 3 to the n is equal to negative 1 to the n times 3 to the n. See that? That's the way we're going to simplify that. And that's going to be over our n plus 1 times 3 to the n. I don't know why that wrote so small there. Right? So now we can cancel this. And now that means we're going to have negative 1 to the n over n plus 1. Why do you keep doing it? I don't understand why it does that every time. Cool. Everybody see how we're evaluating that? All right. Now let's plug in some values and let's see what happens, right? So if n equals 0, what is it going to equal? 0, right? It's going to equal 0. Actually, no, it's not. I lied. It's going to equal 1. I lied. It's going to equal 1. I'm an idiot. All right, cool. And if n equals 1, it's going to equal what? Negative 1/2, right? Yeah, it's going to equal, yeah. So then if it equals 2, it's going to equal 1/3 minus 1/4 plus 1/5, all the way there. So if it is an alternating harmonic series, what does that mean? It converges, which means what for our series? It converges at negative 1, right? So our new interval of convergence now, because of this, is going to be that. So that's the first test that you have to do. What up? Yeah.
Stop there and say this is a harmonic series, then you're not done. Have to compare it. Say, okay, I've got b sub n, I'm going to define it as a harmonic series, and then you have to run this one is a limit comparison test. It's like, oh, the harmonic series diverge, alternating harmonic diverge. This one does the same behavior as this guy. The alternating harmonic divergence. Like, you're not done when you get to this point. You have to compare it to a p series. So if you're not in an exact p series form, you're not done. Does that make sense? Like, I just wanted to bring that up because a lot of people miss that quizzes. That's all.
Good. Cool. All right, cool. So there's our test for negative 1, right? So now it's going to be that interval of convergence. So now we have to test for positive, and that's supposed to be 5. My fault. That's supposed to, wait, no, it's not. This is supposed to be 5. All right, cool. There we go. I'm going to erase that. Cool. So we know it converges for negative 1. Cool. So now let's test 5, right? So now we're going to test 5. That's our new test. So let's plug it in. So we're going to have 5 minus 2. That is going to be the summation. So n equals 0 to infinity. N minus 2 is going to be 3 to the n, right? 3 to the n over n plus 1 times 3 to the n. All right, cool. Well, does that not equal just the summation or the limit of 1 over n plus 1? Right? What does that do? Diverges, right? So because this one diverges, gosh dang it. So this one diverges, which means that the P series converges as x is greater than or equal to negative 1 and less than 5. Does that make sense to everybody? Any questions on that problem specifically? Is everybody good on that problem? You good? All right, cool. So it looks like we're about out of time. I only had a couple more things. I have parametric equations. I don't care. I don't know if you guys have gone over that yet. Won't be on the exam, so I'm assuming you guys won't really care about it. Not right now? Yeah? All right, cool. All right, well, thanks for coming. Huh? That's the question I don't know. I feel like we did last semester, but I don't know if we are this semester because we've been having problems with it.
website? Like yeah, the website. Not the website, sorry.
Now, do we care about the feedback slide? Does that work? Sick. All right, thanks for coming out. I'm assuming I just hit stop share, yeah?
Guys, thanks for this cash.
Of course.